Okay, the student does an experiment to determine the critical angle for glass. So we know that's 42 degrees. At 42 degrees, it'll come in and shine along the side. Any angle greater than that will have total internal reflection. And any angle less than that, it'll just refract. Okay, so there's the basics. The ray of light does not change direction when it enters. Explain which of this explains why the ray of light does not change direction when it enters the block at X. So why isn't it that it's refracted here? And it's because it's 90 degrees to the surface. It will only refract if it comes at an angle. Remember, our angles are always from the normal, but if it's not incident at 90 degrees, it won't bend. And then this one, depending on what it's going through, it'll either bend towards or away from the normal. So, which of these explains why? We're just after something along the idea of it's at right angles, and there we go. So the ray enters along a normal to the edge of the block, 90 degrees. Next one, the student repeats the procedure for different angles of eye, and we can see that there. Describe how the student should use the graph in figure 15 to determine the critical angle for the glass, which we know is 42 degrees, that's bump and along, greater than 42 degrees, bump and total internal reflection. Less than 42 degrees, bump and refraction. Okay, so let's get rid of all of that, and now let's actually answer the question. So, extrapolate and extend the graph. So we're saying we want to find out all this, so we'd have to find out the rest until r equals 90. There we go. So we want to get what is it where the incident, angle is 90 degrees, and then read off angle I. There we go. Tricky question that. So there is, for different angles of I, what do we want to do? Well, for us to determine the critical angle, we want it to be 90 degrees. So that's this basic idea. We want it 90 degrees to the normal. We want the light to come in and exit at 90 degrees. There we go. Figure 16 shows two iron spheres, P and Q. Okay, so the black one is a good absorber. The Q is a poor absorber. Each sphere is the same distance away, perfect, so that's been set. They've got the same radius, perfect. It's switched on the spheres. Explain why the temperature of P increases at a faster rate. So it's not enough for us to just talk about absorption. We know things stay at a constant temperature when the rate at which it absorbs is equal to the rate that it emits. So objects are constantly taken in, so absorbing and emitting, and if that rate is the same, it'll stay at the same temperature. If it's increasing, it's absorbing at a faster rate than it's emitting. There we go. So P is black, which is a good absorber of radiation. Q is white, which is a poor absorber of radiation. And then we can talk about the rate. P will absorb radiation at a faster rate than Q. There we go. Explain why the temperature P reaches a constant value. Now we're definitely in absorption equals emission, the rate of the absorption here. So here it's absorbing more, so temperature goes up, and then it gets to the point where the rate it comes in is equal to the rate it goes out. The rate it absorbs is equal to the rate it emits. So P is absorbing radiation, perfect. It's a faster rate than it is emitting, so temperature increases. Okay, so here absorption is greater than emission, and then here the two are the same. That's it for 4 marks. The temperature levels off when the rate of absorption is equal to the rate of emission.